Okay, let's begin. So, the topic for today is continuation from last time. Last time we learned about classification problem, and today we want to uh, try a new learning method. Um, so we learned about SVM last time. Basically, it tried to find uh, a line that can split the data into positive example and negative example. Today we're going to learn about one class of learning called prototype-based learning. So a little bit of a refresher. So supervised learning, you are given a feature and label pair, and then you want to find a real value function, fx, that will map the feature into the corresponding class label with high accuracy. So that is our goal. So our goal doesn't change, but the way that we um, estimate or model this function f is going to change a little bit. So we want to cheat learning a little bit. So normally when you think about learning, right, you want to generalize the data so that when you see a new data, you know how to handle it. Um, And that is like the new generation of learning. But we want to go back in time a little bit to learn about prototype-based learning. And this type of learning is actually, although the name suggests that it's a learning, but it's not really learning. Uh, and there are many methods in this like type of learning. Um, so the most common one that you may have heard, like in many places, would be KNN, K nearest neighbor, and the rest is um, some extension to um, the K nearest neighbor. And today we will learn two of these five. We will learn about KNN and about LVQ, learning vector quantization. So let's start off with KNN, right? So the algorithm for KNN is quite straightforward, right? In each method, right, there will be a learning part and a prediction part. For nearest neighbor, in the learning part, you do nothing, right? You don't learn anything. Basically, you have your data, you just store your data in the database, right? So that is your learning. It's basically memorizing, right? So you try to remember every example that you have seen so far. And so the main uh, algorithm would be for on the prediction, right? So when we see a new example, let's say X new, right? We see a new example. So when we see new example, we have our database, right? We can search in the database what is the nearest example to this new data. So you can think of each data in the database as a point in space, right? And then when you see a new data, it's going to be a newer point in space. And so you just find the nearest one, and then we make a conclusion that whatever the data that is nearest to would share the same label, right? So the prediction is quite straightforward, right? You find the nearest training example, and then you just say that, well, it's the same label. So what is K, right? In the learning exam, in the name, right? It's KNN, right? K nearest neighbor. So right now, what I write here, I only look at one, right? One closest, and then I just assume that it should have the same label. But for K, I have to go a little bit further. So instead of looking at the nearest one, I look at the K nearest example, right? For example, I have the new data X over here, right? And this blue dot, right? This blue dot is the nearest example. And so if I only look at the nearest example, I would say that, well, X should be blue, right? X should be blue. But if I say that, okay, I'm not going to look at just one, I will look at five. So I have to go a little bit further and find five closest point to X. So now I don't have one, I have five, right? What would be my prediction? So five nearest neighbor, I have four red and one blue, right? I have four red and one blue. So my prediction would say that X would be red. So basically, when you go all the way out to find k number of nearest example, you just do the voting, right? Whoever have the highest number of label win, right? So it's winner take all. And in most cases, your choice of k would be an odd number, right? Why would that be the case? Why can I not pick even number? Why it has to be odd, right? So if it's even number, it can have a tie, right? You have the same number of blue, same number of red, and you don't know which one to pick, right? But if it's an odd number, you are you make sure that, well, one side is going to win, right? This is true for um, the data with two classes, right? If you go to the data with 3, 4, or 5 classes, then this condition is no longer valid, right? Let's say if you have like red, blue, and green, right? You have red, blue, and green, and if you pick k equal to 5, you can still get like 2, 2, 1, right? And then the red and blue can still tie. So our number only apply when your data have two classes. But if you have more than two classes, well, it can be any number now. So that is the KNN, right? You actually didn't learn any function f. There's no parameter, right? The only parameter is how you calculate the distance, right? From point to the data set. So at the beginning, like this method is actually very common, right? Because it's very easy to understand, and the data is not very complex, right? If something that looks similar, it more it's more likely to have the same label. And we talked about decision boundary last time for the SVM. Now, in the SVM, you only have one boundary, right? You have one boundary, one side would be positive, another side would be negative. Now, in KNN, right, you can have a lot of decision boundary. And why is that the case, right? So in each example, right, for example, 1, 2, and 3, if you look at this 1, 2, and 3, right, there will be an area that the point number 1 would be the closest, right? So any point in this area, right, in this area, this would be the like no matter which point that you pick inside this area, the point number one would be the closest. So if your KN is 1 and n, right, basically 1 and n, this is the boundary for this point. And when you have more example, each point is going to have its own decision area, right? And when your new data fall into that area, we'll just assign the label to be the same as the point that is the owner of that area. And the area is going to form the Voronoi diagram. This is mostly in graph theory that you heard this name, like graph theory and computer graphics. But other than that, you probably wouldn't see this word. So in a sense, it's actually more generalized than the SVM, right? Because we can have a very complex boundary, right? For example, like this can be red, this can be red, this can be red, right? And you can have the blue between red, right? Depending on how your data is distributed. So that is the decision boundary for KNN, right? We are not computing the boundary. It's just when we visualize the space, it forms this type of boundary. So it's better to visualize, but when we do calculation, we never calculate what is the equation for this side, what is the equation for this side. We never do that. So these are the example of the KNN, right? So basically you have the blue and the yellow example, right? And this black line is the decision boundary. So you can see that there is like the blue area, like small blue area here, and then the rest would be, you know, quite equal. So this is the 7 nearest neighbor, and this will divide the area, right, into two color, and you can see the decision boundary, right, is very complex, like compared to SVM, it's not smooth. So when we have like KNN and SVM, like these two are the most common method for classification tasks. So what are the challenges with KNN, right? Well, the first one is the distance measurement. How would you measure the distance between 2 points? Right? Sometimes the data is not number, right? Sometimes it can be text, can be image, right? How can you compare the distance between two images? So that would be the challenge. How to choose K, right? This is a very common question, right? You also see this when you learn about K-mean, right? How do we choose K in the K-mean clustering? And what about high dimensional space? Why is it a problem? Right? If the data have like 100 feature versus 1,000 feature, what is the difference between um, the two data set, right? And another one is the large data set, large number of data. So about like 20 years ago, right? Our data is not that large. Like at most would be like 1 million point. But now it's become like 1 billion. So when we have a large data set, we need to find a way to store it efficiently because remember we have to find the nearest point, right? And if we compare one point to 1 billion point every time we have a new example, it's going to be computational expensive. So for the distance measure, the most common one, it works most of the time, is Euclidean, right? Now, to use Euclidean, you have to make sure that all dimensions are in the same unit or scale. If it's not in the same unit or scale, you would normalize the data, right? It can be, you can use standard scalar, or you can use like min-max scalar. So those are the two scaling methods. So this is a very simple one, right? You basically subtract, and then you find the length of the vector. There are other fancy distance, right? We can have weighted Euclidean distance. So basically, you treat each feature differently. So each feature is going to have a different weight, right? This WK. And you can control how important this feature is by changing the value of K. Another one is called cosine similarity distance. So for cosine similarity distance, basically, if you have two data points, you're going to find the vector to the two, and then you find basically this angle, right? And cosine similarity um, often used when your feature vector have the length of one, right? So basically, like all of the point lie into some sphere, right? In some sphere, right? All the data point inside the sphere, right? And this is a common distance for like all of the text data. So you have a choice of distance, right? There are actually many more distance, but these four are the most common one that you would want to try first. So what about dimensional, right? So when you have a high dimension space, points are further apart, right? The more dimension you have, the more distance you introduce. Because remember the distance, right? When you take the Euclidean, right? You sum all of the dimension, right? So if you have more dimension, the distance, the overall distance is going to go up. So when you have high dimension data, points are further apart. And the distance from the point to the nearest neighbor is going to change, right? In one-dimensional case, if you want to find nearest neighbor, you have to go into the distance of 5 over 5,000, right? So you have 5,000 points uniformly distributed in the unit hypercube, right? And then you want to find the nearest one, you have to go into the distance 5 over 5,000. But if you have more dimension, right? Basically, you have to go to like 5 over 5,000 to the square root, the m root of that number. And what does this mean, right? This number is less than one, right? Is less than one. So when you take the square root, it's going to be um, more than the original. So the distance to the nearest point will increase as you introduce more dimension. Well, another one is efficient indexing. So we want to find a clever way to store the data so that we don't want to check uh, the distance for our example, right? For example, if I have this new point, I don't want to compare this point to every point to know which one would be the closest. So one way to do this is to use KD tree. This KD tree is a data structure um, that store the point in tree-like structure, right? This is the tree in computer science, and basically you have a root node, right? And then you have like outer node, and what you have is when you want to find the nearest point to the new point, you compare the point into the root node, and each root node is going to tell you what point is currently on and what axis it actually splitting. So at the root you have point 35. So at the root you have this point 35, and then it split the y-axis, right? So when you have the new point, let's say you have the point 22, probably somewhere around here, point 22. You compare this point to the root node, right? And then you check if it on top or on the bottom, and then you go to each one of them that is closer to it, right? So this is how you search, right? If you have this green point, right, you can after you split twice, you can actually discard some of the area that will never have the point that are closest to it. So the idea is that when you pick the region, so basically one point is going to split the area into two regions, right? And depending on your point fall into which region, you can disregard the other region, right? And then you can go and then you keep going because the area will keep dividing in half at every step. So this is going to speed up the search by a lot, right? If you have n number of data, the number of time that you have to compare the point into the point in the um, database will be log n, right? Because um, every time you compare a point, you discard the area, like half of the area. So half of the point is going to be not considered. So you throw away half the point every time. And so the number of times that you have to throw away point such that you end up with one point, which is the nearest neighbor, would be log n. So what is the good data set for KNN? Um, you want to have a lot of training data, but not too much. Basically, anything below 1 million would be good fit for KNN. For dimension, you want something less than 20 per se. Um, it would work well in the KNN. And the advantage of KNN is that it's very fast at the training stage because we never train, right? Basically, the training part would be to build this KD tree, right? To transform the data into this tree-like structure. That's the training part. And this building is actually very fast. And you don't have to learn the predicting function, right? Your predicting function would be find the closest point, and then you just answer the same label. The disadvantages of KNN would be like it's very slow at the query time, because have to um, every time you have a new data, you have to compare point into your KD tree. So it's not suitable for commercial because KDD have to be stored somewhere. And if you have like 1 million data, it's not going to fit in your device. So you have to have like a server that can have like store all the data, and then you have to make a query to the server every time you make a prediction. So it's not portable. And it's not good in the highly correlated dimension. So what this means is that um, if the if the class like overlap on top of each other a lot, um, it's not going to work very well, right? If you look at this image, right? If we have like only the data in like this area, like when the blue and the yellow are like interchangeable, then it's going to be really hard for KNN to produce a reasonable result. Okay, so let's try KNN. So we actually have a library for KNN that we can use. We're going to use the new data for today. We're going to do the flower classification. So for flower classification, we are going to use image. Okay, so up until now, we don't have data image yet. So we'll try the image first. So I'm gonna start in Colab. So if you have a computer, you can code along. So we start with the data set. And the data set that we want to use uh, flower data set from TensorFlow. Now in Colab, the TensorFlow already um, installed for us, so we can just use the TensorFlow dataset right away. So we start with import, right? We want to import TensorFlow as the TF, and we also want to import TensorFlow dataset as TFDS, right? So we have the TensorFlow and the dataset, and then we want to load, right? We want to load flower dataset, right? So we say dataset and then information equal to tfds dot load, and then we have the tf flower. And this is the dataset for flower image. And we want to use so there will be train and test dataset. So we can say train dataset equal to dataset train and then test, right? So we have train and test. So let's try to visualize what image, right? How would it look like? So we can say uh, we can import uh, the matplotlib as PLT. This is going to draw image onto Colab. So we're going to go through maybe a couple of images. So in the train dataset, we can say for image and label. So each image going to have a label, right? Basically, which type of flower. Um, and say we for image label in train dataset. I'm going to take two, right? I'm going to show you two images, right? Basically, you can specify the number of data from the dataset that you want to go through. So for each one of them, uh, I'm going to print uh, the shape, right? I want to print the shape. So image dot shape, and then the label, right? And then uh, I want to plot one image. So I could say plt dot I am show. So to show the image in Matplotlib, you have to convert the image into NumPy array. Um, Normally it's like this one is enough. This one is just make sure that it's unassigned int 8. So we can run this. It's going to load the dataset and then print the two images. So this is gonna take a little bit of time because it's the first time that we run, right? It's going to do download the dataset. It's about like 200 megabytes. Uh, so there's no train, no test dataset. Okay, that's fine. So we have two images, right? We have this image. We have the label. I think this is the label number 2, and then we have the label number 3, right? So we have this couplet tulip, right? And then we have this probably sunflower. So as you can see, the image shape, the size of the image is different, right? This image is like 333 by 500. This image is 212 by 320. So we have this image. We want to classify, right? We have all this data. We want to classify. So the question is how we are going to classify, right? If we use KNN, we have to compute the distance, basically distance between this image and this image. How would we compare the distance between two images? And another thing is that each image have different dimension, right? So we have to do some transformation, right? We want to change the image into a feature vector, right? In today application, people would use like neural network to do the to do the classification. And in every neural network, it is require you to crop the image into the same size. It's basically is 224 by 224. That is the most standard size of the image for the neural network. But we don't have neural network yet. So we want to use KNN. So we need a feature vector. So in the past, people would create an algorithm to extract feature on the image. So what are the features from the image, right? So maybe there is a curve, right? This curve right here, or maybe there's a line. Maybe there's a change in the color. So every change is to be considered a feature. So we have a feature extraction using computer vision, right? So right now we have our data. So next we want to build a function, right? So we want to create a function that convert images into a feature vector. And in computer vision, there is a technique called feature extraction, right? So we want to use feature extraction from computer vision. And this feature extraction, there are many methods for feature extraction. The most common one are shift and op, right? These are the most like successful feature extraction algorithm. So we're going to use ORP for this one. So we start with we define a function, right? So we want to uh, image two vector, right? And then you want to get image as the parameter. And then we want to uh, use the library. So we have to do the import, okay? So we import CV2, which is the library for computer vision, right, as CV, and then we also have NumPy, right? So first of all, we have to load the feature extraction algorithm. So we want to use ORP, right? So we can have feature extractor equal to CV dot ORP, right? And inside of you can specify the number of features you want. So if we look at the OP from the CV2, it's oriented fast and loading. Um, you can specify the number of feature, right? It's going to be of create. So I have to do the of create, right? And I believe, let me see, the of create should have uh the op class, right? And then we have the op create, right? So you can specify n feature, the maximum number of feature to retain, right? So we can say n feature equal to 5,000. So basically, what we have is we will use this extractor to extract the feature point from the image, but we only keep 5,000 of them, 500 of them. And so now we have the extractor, right? We have to first check if the image is a grayscale or not. So in every uh, feature extractor algorithm, it is required that you transform the image into grayscale. And so to transform the image into grayscale, you have to check first if the length of the image uh, is going to be, actually we have to convert into the numpy first. So we have image numpy equal to image dot numpy, right? And then the image in the numpy format, you can check if the shape is equal to 3. So if the shape is equal to 3, it means that it is a RGB image, right? So this tell that the image is RGB. So we have to convert to grayscale, right? And the way that we convert to grayscale, we use the CV color. So we have image underscore numpy equal to CV dot CVT color, right? And then you set in the same color, and then you change it to RGB to gray. And then after you convert this into the grayscale, you can extract like key point and descriptor equal to the feature extractor dot detect and compute, and then you would change this into the numpy array, and then you return. So this is the function that you convert an image into a feature vector using ORP feature extraction. So we can try, let's try one image, right? So we have for image label in train dataset dot take one. Let's try one. And then we have feature vector equal to image to vector image, right? And then we print out the shape and also print out the label. So we have 532. So why is it 532? So here the number of features is actually the number of feature point on the image, and each point will have a descriptor, basically explain what kind of point is, and each one of them will have the 32 number as the description of the point. So we have 500 by 32. So every image is going to have this vector. So we can flatten it, right? You can flatten, right? Can I flatten this one? Let's see. Yeah, so you can flatten it to get 16,000 dimension, right? So normally we would prefer the feature vector to be in one line. So we like flatten the entire um, descriptor. So we have our feature vector, right? We have the function to convert image into a feature vector. We also have our data set. So we can start KNN, right? So we want to perform KNN on the data set. And before that, we have to first because we already have train, right? Because we tried last time and then there's no test keyword. So we actually train data set. So we have to split into train and test for um for checking accuracy. So we want to split the data set into train and test first. So we have uh so we have to have the data set, right? So in the train data set, we map each image into the feature vector, right? And then actually this one is shuffle and batch. I think we don't need this one. We can try uh, to import I think from sklearn dot I think 10 import. Is it? I forgot what is it. Which one is the 10 test split? So maybe if I put it under here, is my from okay model selection. Model selection, I import 10 test split. So we convert the dataset right into the vector. So we have so this would be I would say the dataset, but it is vector form. Just so that the name is clear. So when we have this, we can do the uh, x and y. So for each image, um, we will have the label, right? In the vector, we have image into x, and then we have the y as the label. And then we can say x10, x trade. We use 10 test split, and then we pick the random state. So we have split the data into train and test. Uh, so what we want is we want to perform KNN on the data set. So we have to pick K first. So let's try K equal to 1, right, as a example. Um, so in sklearn, we have the K neighbor classifier, and so we can just use it, right? K neighbor classifier, and then you specify the number of neighbor. And then you fit the x10, x test, as well as you can evaluate, right? Evaluate on test dataset. So we get the metric, which is the accuracy score, right? And then we have the y prediction equal to our knn dot predict x test, right? And then you say the accuracy equal to the accuracy function. You put y test and y predict. It's going to compute the accuracy for you. So if we run this example, so what happened? Has no attribute numpy. Okay. So I think this the train dataset might already be the numpy. Is it? No, but it should have numpy, but it doesn't have as int. So we convert the image into numpy. Okay, that's strange. So the train data, right? So we we run this, and this one. So it doesn't have the numpy. That's interesting. Okay, let me check. Uh, so when we are here, maybe if I say only take like 1,000, maybe it will have a better result. No, no. So if it doesn't have numpy, can I comment out this line and use the just use the image? So it doesn't work in this case because it's not in the numpy format. So this one work, but this one doesn't. So maybe the map part. Um, we are going to do uh, this in a harder way. So we have to do the for loop, right? Basically for each image and label. So we do the same thing as this one, but without the take. So we use all the data set, right? We have the feature vector, and then we append the feature vector along with the label. So let's see. So this one does work. Okay. Right. So this method, let me write a comment. So we convert all data in dataset into feature vector. And then so this one we would split dataset into train and test. So we have, so there are some image that doesn't work, I guess. Let me run it again. So this is gonna take a little bit of time. So, okay, so this one, um, in the data set for image, the request array has inhomogeneous shape after one dimension. So maybe we have to change this. So it has to be um in the vector, or because it's become array now. So we use this instead. Okay, let's try. Actually, we haven't checked how many data do we have, how many images and class, but we will try it again. So it doesn't work again. So we have the dataset vector. We append this in, and then we want to try looping, setting an array element with a sequence. Hmm. So maybe we don't set this and we start with X and Y, right? So X is the array and then Y is this. And instead of doing that, we just do it at the same time, right? So we have X dot append feature vector and then Y dot append label, right? And then perhaps we need to convert into the numpy array. Okay, let's see will this work. So this one okay, but this one is not. So maybe it's already in the numpy, maybe. So let's look at the X. So we actually got X for sure. So we want to, let's try to pin the X out. How would it look like? So it's an array of array. All right, so we have this for one image and then so on, right? So if I pin shape, so it doesn't have shape because it's a list. Okay. So length of X should give me, so this should be the number of data that we have. And so we want to convert this into numpy array. So let's see. So normally you would be able to do this. So if I say length of X 0, okay, so one one data will have 16,000 feature. Okay. And so we need to make so it's a list of lists, but we cannot convert into numpy array. So x numpy is equal to x. So this one give us this error. So let's try to ask the chat. So it suggests the suggestion would be we change the type into float 32 before we convert. So I think for y, um, numpy array for y shouldn't be matter because like this one passed, right? But this one is not. And had the feature length to a fixed length. Ah, I see. So we just use this instead. Okay, we are going to trust the AI to fix the code for us. Let's see if this works. Right, so this would be something that you would see like when you work on the data set, when the data set come from like different library and then you want to use it in another library. So you always have to do the conversion. So this one doesn't help, or it does not define, or because I didn't import it. Okay. So I have to import this one, add sequence from TensorFlow. Okay, so we have the accuracy. So the accuracy is 26%, right? Is very low, right? But we only use k equal to 1, right? We only use k equal to 1. So before we make change, let us look at the data first, like how many data. So we know that we can print the x uh x ten and x test, print the shape. So x train we have about 3,000, and then x test we have this. So we will see how many label print unique label, right? So we have the numpy dot unique. So we have 5 classes of flower. So if you take a guess which flower is from, you would be correct 20% of the time, right? Because you have 5, right? So it's 5 in one chance that you will get it correct if you guess the same flower every time, right? So the accuracy is slightly better than chance, right? So the chance is like 20%, and then you have like 26%. So if we increase k, let's try k equal to 7, and then rerun the algorithm. So because I don't want to convert this again, I'm going to uh, move this into a new block so that I don't have to re-download the dataset again. So for k equal to 7, you have a small improvement, right, to 29%. So let's try very large k, like let's say 19k. So the more k you have, it's gonna take longer time. So the more k you have, you will have the higher accuracy. It's gonna fall off at some point. So you can plot like k and then the accuracy, and then you can pick the base k, right? So that is one way that you can choose k. So that is the k and n part, right? So I've shown you how to convert image into a vector and use that vector for classification. So we're gonna come back here and then learn about another method, like we call we want to cheat less, right? So we want to learn to actually learn something now, and to actually learn something, we have to make a representation, right? We have to make a model, a representation. So in KNN, you only just find the closest example, but now we have to make a representation. So the representation in the early day, the representation would lie in the same data space, right? Basically, it's another data point, but this representation may not be the real data. It's a made up data. It live in the same space as the data, and then you can do something with it. So the good thing about a representation is that you don't have to store the entire data, right? Once you have the representation, you only use the representation. So this representation can be thought as a generalization of the data. Basically, you just use a lot of example to shape the representation, right? So that you can use the representation for uh, prediction tasks. So one of the easy method to run a representation is called learning vector quantization, LVQ. Now in the LVQ, we have uh, a prototype, basically a vector, right? A vector, right? WI for each class, right? This vector is in the same space as the data. So when the vector is in the same space as the data, what happens is that you can compute the distance between this prototype and the data point. And the general idea of this algorithm is that you want to slowly move closer to the point of the same class, or you want to move further away from the point of different class, right? So for example, you have this prototype, right, WI. You have a positive example and a negative example. And let's say this representation, it was supposed to be for a positive class, right? So we have positive and negative example. What we want is we want to move this point closer to the positive class, but we want it to move away from the negative class, right? Right. So we want to move closer to the positive, but move away from the negative class, right? And when we have this representation, you don't have to store the data anymore. When you have the new data, you just calculate the distance from this data into the closest representation. So the way that we move the point, right? We have the update function, right? So for each example that we have, we find the closest prototype, right? Basically the vector, the representation of the class. So once we find the closest prototype, we do the update for that prototype. the same prototype that is closest to that point. Now, the update function will depend on whether or not the, the point x, y, and the prototype share the same label or not. If it have the same label, right, you use this equation. If it's different label, you use different equation. So how does this equation come about, right? So we have, let's say it had the same class, right? Let's say uh, we have this vector, right? We have this prototype for a positive class, right? And then the closest point would be this positive example. You want to move this point into this direction. So basically, whatever we have, right, we have to add this direction, right? You want to add this direction. How do we compute this direction, right? In vector mathematics, to compute the vector from the current point to the target point, basically you have the target minus the source, right? So that's why our target is xi, right? This is the xi that have the same label. So xi minus the prototype, right? This equation is going to give me this vector, right? And instead of just adding the direction directly, we have a coefficient, right? This one is called learning rate. Now, this coefficient will control how much the point move, right? You don't want to move a lot, like you don't want to just move to this point at all because you are going to jump around between point. So it's better if you just move closer, but not a lot because you still have other point that you have to be to worry about. So that is for the positive example, right? And for the negative example, actually I have this one, right? So for the negative example, right? Let's say um, I have my model, right? For the negative example, but the closest one, let's say is this point for the positive example. I want to move this point away because they have the different label, right? I have the prototype for negative class, but the closest point to it is a positive class. So I want to move this point away from it. And the reason why I want this to move this point away from it is I want to move this point away from it so that this point at some time it will no longer be the closest point. We want to change the closest point of this representation to be the same class. So whenever we see the closest one that is not in the same class, we want to stay away. So when we stay away, that point will no longer be the closest point, and you will have the new closest point. And hopefully that new closest point would be the same class. And if it's not the same class, then you will still move away. So to move away, right, basically you use the same vector, right? You have this vector that is moving toward. So to move away, you basically use subtract, right? Instead of adding, you subtract. So you are going to in the opposite direction. So that is the update function. So we go through this for every data, right? For every data we have, we do the update function for the closest prototype. So we want to talk about the learning rate, right? So eta is the symbol for the learning rate. Now, The learning rate is the hyperparameter that uh, specify the size of the step we take. And if you have a high learning rate, right, you can overshoot the, the correct answer. And this will lead to um, oscillation and also divergence when you try to learn something, right? So basically, if you set the high learning rate, the point will jump around by a lot, right? And it will never be stable. Now, if you set it too low, right? It's too low, it's gonna move a little bit at a time, right? And it's going to lead to a slow convergence, and sometimes you would stuck in the local minima, right? So this is about the same when you do a Newton method, right? So the best way to pick the learning rate is to do the adaptive learning rate, right? Because at the beginning, we want it to learn really quickly, right? Because at the beginning, when we start our prototype, we don't know anything about the prototype, like where it should be. So because of this, we want it to move very quickly to the correct position. So at the beginning, the learning rate um, should be high to speed up the learning process. But as the times go on, you want the step to be smaller, right? So as it gets closer to the correct position, you want it to move very slowly. And we actually have this equation for the learning rate, right? So the learning rate as time t divided by 1 plus lambda t is going to be the learning rate for the next iteration, right? So every time you update the learning rate, update the vector, the learning rate will keep uh, smaller and smaller. And this lambda is also a hyperparameter that control the rate of decay. There are three common values that you can try, and this t is the time step. So basically, if you do one loop of the algorithm, t is going to be 1. If you do 2 loop of the algorithm, t is going to be 2, right? So t is going to increase over time. So that is how you do the adaptive learning rate. Nowadays, we have adaptive moment estimation called ADAM. And ADAM is the most popular adaptive learning rate method because in practice it works very well and it often lead to faster convergence. Um, the equation for ADAM is not very complicated, but it's purely mathematics. So I'm not going to explain the equation for ADAM here. You can just look online. And the purpose of ADAM is to use for training the deep learning model. So in almost all machine learning library, you're going to have this ADAM. So you don't have to specify the learning rate. Well, you could specify the initial learning rate, and you would use ADAM to pick the new learning rate for the next iteration. But for here, for now, we are going to stick with this equation because it's easier to explain and easier to compute. So epoch, what is epoch? Have you heard of the word epoch before? So epoch is a unit of time in the algorithm. So when you go through each example in the dataset, right? Go to all except for once. We will call this one epoch, right? So here, when we have the algorithm, right, we say for each example, and then we do this thing. So after we finish this whole for loop, the time is going to pass one epoch. Right? It's the unit of time in machine learning. So when we go to all example, once, that's one epoch, right? And the epoch um, is going to be one of the hyperparameter, right? Depending on how many times you want to update um, the prototype, right? You want to go to to go to all example how many times, then you can set the number of epochs. In some cases, you can change the termination, right? Sometimes you set epoch to be, let's say, 500, but at around 300, you notice that the solution, the change to the solution is very small. So you can also terminate early, right? So epoch is, you can think of it as the maximum number of iterations that you want the algorithm to run. So that is the definition of epoch. So how do we fine tune the hyperparameter, right? So we have the learning rate, right? We have also the lambda for the decay. We also have the epoch, right? So how we should fine tune the hyperparameter? So the most common method is called trial and error. Basically, you try each combination, you see the result, and then you just pick the best one, right? And to do that systematically, you want to split the training data for cross validation, right? So basically, you split the data into maybe 5 parts, right? And then for each part, you hold out, and then you use the remaining 4 to train, and then you get 5 accuracy, and maybe you do some average. You can like drop the maximum, drop the minimum, and then you take the average of the middle 3. That would be the accuracy for one set of parameter, right? And then you do this for other one. So it is important to note that when you fine tune the hyperparameters, do not use test data, right? Because it's cheating. Normally, you would fix the hyperparameter before you use it on the test data, right? So whatever it is, um, you have to live with it. So this is how you would fine tune the hyperparameter. So let's try LVQ. Now LVQ, there are not many library, so we are going to implement it by hand, so that we can see each of the step, like in the code, right? Because up until now, we use the library, right? We use the classifier, we just like dot predict dot fit, and it's gonna do everything for us. Now we want to do the LVQ, but we are going to read by hand. So by hand, I mean we have to write the code for the entire algorithm. And I will show you step by step how to do that. So we have extract and extract from the data already. So we're going to start the algorithm. So if we go back, look at the algorithm, right? So we have to start with creating the prototype. right? So we want to perform LVQ on the data set. So we start with prototype, right? So we have 5 classes, right? We have 5 classes in the data set. So the number of prototypes should be at least 5, right? One for each data set. You can have multiple prototype per class. That is also okay. I'm going to use um, the prototype for, I'm going to try to have 2 prototypes per class. So we have 5 class. If we have 2 prototypes per class, so I have to create 10 prototypes. And I just create it at random. So I'm going to say numpy dot random dot rand, and then 10. 10 is the number of prototype, and then the second number is the number of feature, right? So I have this number of feature, right? So I have to match the number of feature of the data. So we have this many number of prototype. And then I want to create a function, right? I want to create a function, but I would have prototype class, right? So I want to have this class like 0, 1, 1, 2, 2, 3, 3, 4, 4. So basically I'm assigning the class for each prototype. So prototype number 1 and number 2 would be class 0. Prototype number 3 and 4 would be class 1, right? So I have this the class for each prototype. So that I can check if the point is in the same class, I can do the update correctly. And for each example, I have to find the closest prototype to the point. So I want to create a function that will return uh, the index of the prototype that is the closest, right? So I will create a function uh, find closest prototype, right? And I would have x and prototype, right? So we have the data x, and then we have the prototype, which is going to be this parameter. And there are many ways to do it. You can use the numpy, the norm distance, right? Basically, you subtract x to the prototype, right? For each prototype, you subtract, you calculate the distance, and then you return the argmin, right? The minimum distance, right? So this will give you the index of the point of the prototype that is closest to that point. So this is the find closest prototype. So now that we have the function, so let's say a function to find the closest prototype given data x. And then the next one, we have to specify all the hyperparameter, right? So we have the hyperparameter. So what do we have, right? We have the learning rate, right? Let's say it's 0.01. ePOS maybe 100 at the start. Um, we want to have the decay as well. So we have the, I think it's called lambda, but the lambda is a keyword in Python, so we cannot use the word lambda. So I'm gonna use the decay rate. is that, right? So the decay rate here, right, is the lambda in the equation. So let's say it's 0.1, right? So we have all of the hyperparameter. Now we are ready to train the model, right? So our model is this one, the prototype. So right now is in the random place. So we want to move the prototype into the correct position. So for the algorithm, right? So we have to go through each example, right? So we have to go to each example. So we can say for so we start with epoch letter for I in range length of X train, right? So we have X and Y, right? And then you find the closest prototype. So once you find the closest prototype, you check if the prototype is the same, right? So if the prototype class, right, of the closest prototype is equal to the Y, right? Is equal to the label of that point. If it's equal, right, you would move this point, right? So this is the same label, right? This one is the different label, right? So this is the update step. So if it is the same label, you basically plus equal. So plus equal is basically the same as you add this one to the same variable. So we use plus equal, and then we have the learning rate multiplied by um, the direction, right? So this x minus the prototype would be the direction. So if it's the same label, you move the prototype closer to that point. If it's different label, you move the point away, right, by using the -1. And after you compute the step, right, you can update the learning rate. Now, normally, it also depends on how you define uh, the timestamp, right? So this can be timestamp like for each for each point. It can also be the number of epochs, right? So you can do either way. So this one, I'm going to not update yet, right? So this is the learning method for the LVQ, right? You go to each example, you find the closest prototype, you check if the prototype have the same class as the data, and then you either move closer or move away. And this entire for loop is one epoch. So we have to do this for 100 epochs, right? So I would get for epoch in range epoch, right? So I want to do this for how many number of epochs that you pick. And after I finish one epoch, I can do the update on the learning rate, right? So I can say learning rate, right? It had to be divided by 1 plus lambda t, right? So we have learning rate dy equal, right? 1 plus the decay rate times epoch. So the way that epoch start, right? So basically you start with 100, right? So epoch will go from 0 to 99, right? So most of the time if epoch is 0, you have the same learning rate, right? So basically, you want to update the learning rate before, because at the first iteration, epoch is 0, you get the same learning rate. But when you start the second iteration, epoch become 1, and then you have the lower learning rate. So this is the training method, right? And then we can run to train. It also worth noting that you should be able to print the number of epoch, right? If epoch mod 10 equal to 0, you can print the number of epoch. So the print here is just so that you know how many epochs have passed, just to make sure that like the algorithm is running. So this is going to take a little bit of time because we go to our example like 100 times. So while we let it train, we are going to do the prediction part, right? So we haven't done the prediction part yet. So we want to predict, right, the test data using the learn prototype. So because we have this function, find closest prototype, right, we can use that function for the prediction. So we can say, we can start from y predict equal to the empty set, and then we can go to each of the training example. So for I in range of the x test, right? So we have x equal to the x test at the I, and then we compute the closest prototype, right? And then whatever the closest prototype you have, it class, like the closest prototype, the class that it belongs to is going to be your answer, right? And then you append it to y predict, right? And then you can print the accuracy, right? So you can print the accuracy. So we have the accuracy score for y test and y predict. So right now we are at 80 epoch. So it's almost done. Okay, so it's finished. And then we can try to do the prediction. Incomplete. Okay, I forgot the last closing parentheses. So you have about 24%, right? 24.9%. So if we compare to KNN, right? So it's still not as good as KNN. Um, the way that you can change this, right? You can change the training method, right? You can change the hyperparameter, right, to find the best one, right? Because in KNN, you only have K, right? But for here you have uh, 3 parameter, so you can change it and then try again. So this is how you would train a model by hand, right? Basically, you do every step by yourself by not using the library. And this is going to be an important skill when we move on to um, the neural network, because most of the neural network, you would try to write the same thing. There are some package that you can use, but that package is often outdated very quickly. So if you can write the entire training process by yourself, um, your code is going to stay the test of time because the library that you didn't use the library. So whatever the new data you have, you can also use the same learning method, right? So the takeaway is that um, for the learning, you start with the number of epochs, and then you go to each example in the dataset, and then you do the update function, right? That is the only step in all the machine learning algorithm. Right? It doesn't matter if it's a neural network or SVM. Then the way that it designed is will be the same step. So any question for uh, the code? So hopefully this should actually give you some insight of the algorithm, the library that we use, like because before we only used like dot fit, dot predict, right? But now we actually write out the entire algorithm. And I picked this algorithm because it's the easiest to write, right? For the three more algorithm for in the same class that I haven't shown you, it's going to be a little bit more complicated. And when you write code, it's going to be a lot messier than this one. Right. So here you can also increase, right? You can increase into like if you think that um, this class, like you can also show the conversion metric, right? I can show the confusion matrix. So the confusion metric is basically um, the class, right? Basically, it's going to show you how much the prediction class and the correct class correlate. And when you look at the conversion matrix, right, you look at the diagonal, right? So class one, you actually have a good accuracy, but class two, um, like class ID 1, class ID 3, class ID 4 have a very low accuracy. And if you identify the low accuracy, what you can do for this method is that you can increase the number of prototypes. Maybe having only 2 prototypes for this class is not enough. So you can say you can increase to like 12 and then you can add one more. So you don't have to have the same number of prototype per class. You can have you can have a different number of prototype per class, right? So you can look at the accuracy and then you can make a judgment that okay, this one maybe you need more prototype to explain this class better, right? This one maybe need more, this one maybe need more. So you can use the conversion metrics to change your initial configuration. So that's it for today. We learned uh, two methods, right? We learned KNN and LVQ. And then starting next week, I have I haven't checked my schedule, but it should start to be um, in the neural network territory. So don't forget to get started on your assignment 3. It's the multi-class classification. I think you have about 1 more week, 1 or 2 more weeks, if I'm not mistaken. So make sure that you complete that. So if there are no further questions, I will see you again next week. Thank you.